All right, our ultimate talk in this session 3 here is Jesse Rodriguez from Stanford University. His field is plasma physics and optics. His advisor is Mark Capelli, and his practicum was done at the Princeton Plasma Physics Laboratory. All yours.
All right. Hello, everybody. Today I'm going to talk about the inverse design of reconfigurable plasma metamaterials for optical computing. We actually talked a little bit about this yesterday, but conventional computing technology is beginning to hit a physical limit. So when I came here, my first year of the fellowship, there was a lot of talk about heterogeneous computing platforms, GPUs, application-specific components. We've had to move in that direction because we're hitting this physical limit with our transistor gate width. And so in order to perform computational tasks, these sort of conventional technologies push electrons around, they generate heat, and they also place a speed limit on the signals equivalent to the speed of light in metal. Now, we talked about some alternatives yesterday, like there's a lot of hope for quantum computing. But today I'm going to talk about a different way that we might be able to accelerate our computing in the future, which is by manipulating electromagnetic waves in order to carry out computational tasks. In my lab, we do plasma physics research. And so I want to explore how we might use plasma to carry out optical computing tasks. Now, one example of an optical computing device would be like what you see here on the top right. It's what we would call a diffractive deep network. This is from the Ozcan group at UCLA. And the idea is that you send in an input object, say like this 5 here, and then these very complex diffractive layers will redirect the light into the correct detector on the other side. So instead of like a convolutional neural network, which is doing a bunch of matrix vector multiplication, the computation is occurring at the speed that it takes for the light to pass through the device. So it's very fast. There's no component heating because there's no direct ohmic losses. And you can get a very high bandwidth and speed because you can encode a lot of information into different colors or frequencies of light and send them all through the device at the same time. The key benefit of the use of plasma as an optical device is that the electromagnetic response of plasma is dynamically tunable, which also allows a single device to serve many functions. You might create a device like this, which is just a bunch of plasma discharge tubes in a wood pile configuration. And by tuning the discharge that you supply to each of these plasma elements, it can then perform a bunch of different functions. So today, we're going to talk about how inverse design can be applied to design plasma metamaterial devices that perform various optical computing tasks. But before we do that, I want to talk a little bit about plasma's unique electromagnetic response, which is sort of encoded by its permittivity. So when an EM, this is just sort of like physics 101, when an EM field propagates into a medium, it creates local displacements of charge, which results in like a dipole moment. Those dipoles begin to oscillate, and then they radiate EM waves, which in turn incites the dipoles next to them, and you end up with this sort of plane waves traveling through your medium. And by observing or calculating how your EM waves are exciting these dipole moments in materials, you can calculate the permittivity, and in simple materials, it's very recognizable. It's just equal to the index refraction squared. So just keep that in mind. The permittivity of plasma allows us to tune its electromagnetic response. So the permittivity of plasma is up on the top right here. If you have collisions or loss in your model, it's here. And then if you collisionless, it's like the rights. But it depends on this thing called the plasma frequency omega p. And this is a function of the plasma density, which you can change by basically supplying more power to the plasma. Either if it's a laser-generated plasma, you'll turn up your laser power. Or if it's a discharge like what we have in our devices, you just supply more current to the discharge. So by tuning the plasma frequency, we can make the elements of our devices either stretch or speed up EM waves or act like a reflective metal. So in this plot here, the blue line is just the collisionless plasma permittivity. The orange line is the real part of the collisional model, and then the yellow line is the imaginary part of the collisional model. So basically, depending on what the plasma frequency is in reference to what your operating frequency is, plasma can either stretch waves, like it's like for an underdense plasma, if the plasma density is low, since this is in the numerator here, your permittivity is greater than 0. So your index is between 0 and 1. If your density is very high, the permittivity becomes negative. And so we talked about how the permittivity is like the index of refraction squared. That's in like the index of refraction is in the exponent of your exponential. So if the index of refraction squared is negative, the index of refraction is imaginary, you get evanescent waves and you get reflection, and it's performing like, it's acting like a metal. Another thing to note here is that when you assume no collisions, the refractive behavior of the plasma might be approximated quite poorly. So you can see this big gap between the orange and blue lines. The overall frequency dependence that we see here is an extremely important aspect of plasma materials, and we'll talk a lot more about that. So to create our device, we use inverse design. So up until now, experimentally realizable devices produced via inverse design were binarized. So you either had material there or not, and you can create these via like laser etching or lithography. And these devices are also static. They perform one function. Plasma materials are nice because the plasma density and then hence the permittivity of each of the elements in the device can be dynamically and precisely tuned through a continuous range of values. So this gives us an infinite configuration space for trading purposes and a possibility for a single device to serve multiple functions like we mentioned before. So our device is very simple. It's just a 10 by 10 array of plasma discharges, cylindrical discharges like rods like you saw in that earlier image. Then you have these input and output waveguides. You have a source on the left, and then these probes on the right that we use to calculate the objective function for our optimization algorithm. On the left, this is just like a waveguide. You either send the light through and preserve the input mode straight through or through a 90-degree bend. And then on the right is a device called a demultiplexer, which will take one frequency of light, omega equal 1, this is non-dimensionalized of course, and turn it or direct it to the top exit, and then it will direct omega equal 1.1 light to the bottom exit. So we optimize the PMM with the plasma frequency to elements as the parameters. And we do this via forward Moore differentiation. So you basically compute the gradient as you go, and then do as you compute the simulation, and then compute the back propagation. This is using software developed by our collaborators called Ceviche. So you take your parameters rho, you map those to your plasma elements to come up with this relative permittivity domain. You apply Maxwell's equations, do your physics, you get your fields out, your solutions. And we train our devices using our lab's own computing cluster and on Stanford University's own HPC research resource, Sherlock, which is a pretty nice resource to have. It has a total computing power over 3.5 petaflops, which puts it in the top 500, which is nice to have, as I said. So here are some of the results. So what you're looking at here is on these left-hand figures. These are the field intensity. And then on the right, you have the relative permittivity domains that produce that intensity. The darker red that the plasma elements are, that's like the higher the density is, because the permittivity is lower. So a mode-preserving low-loss waveguide is the simplest objective for this device. Another thing that I didn't mention earlier is that the TE and TM that you're seeing on these plots referred to the different polarizations, transverse magnetic and transverse electric. Since the device consists of vertically oriented rods, the response is polarization independent. So if you send in light that has the E field pointing in this direction, you're going to get a different response than if it's aligned with the rods. So a couple things to note just from these results is, in general, this sort of permittivity distribution that we get here is really unintuitive. So if you were going to go and design a straight waveguide, say, and this is what we've done in the past when you make a waveguide, like a photonic crystal waveguide, for example, out of plasma elements, you would just turn the plasmas in the place where you don't want the light to go to the highest density possible, because you'd be trying to approximate a metal waveguide. But it turns out that when you applied inverse design to this, we found that's not actually the best way to do this. And when you're actually trying to bend the light or work with TE polarization, which is more difficult in general, you end up with these really, really non-intuitive plasma density distributions. And so it's quite interesting. Now, the operating frequency must be modest if we want to ever have sort of experimental feasibility of these devices. So on the operating frequency, we talked the plasma Permittivity involves this ratio between the plasma density and the operating frequency. If the operating frequency is too high, you're putting a big, you're requiring your plasma density to also be high to get the same sort of structures and performance. So we also wanted to make sure that these devices worked when our operating frequency was low, our plasma densities were low. And in each of these cases, with the exception of the TE cases, which do struggle, and we can talk more about why they struggle if you guys are curious later during the question period. Especially in the TM case, they perform really well, and then in all these cases, the plasma density is extremely reasonable. So this was encouraging, and then the demultiplexer also. Did very well in all cases except for the low frequency TE case. Now, demultiplexing in general is an extremely important function for achieving a high degree of parallelism in optical computing devices. And a lot of these devices you send in, you encode different information in different frequencies or colors of the light and send it through your device, and it's redirected accordingly. So performance is consistently good with the exception of the TE designs, like I said. And to progress toward experimental realization, we refined our plasma element model. So we saw those results. Those were with the idealized model, and we thought, okay, let's see if we can actually build one of these devices. So we introduced non-uniform plasma density profiles, collisionality. So now we have a collision term in our permittivity, as well as quartz envelopes, and we also ensured the devices were resistant to random perturbations. With the non-ideal factors considered, the waveguide and demultiplexers still perform well. There's a little bit more loss, and they're also a lot more difficult to optimize. And we also just tossed out the TE case in this case because we knew we were already having trouble with the idealized elements, so that wasn't going to be likely to work. So these require a lot more careful design of the input of the initial parameters, the optimization, and also the parameters of the optimization algorithm. But nevertheless, they're still performing quite well. And then they're also very robust to random perturbations. So we applied the sort of mean zero Gaussian noise that's scaled by the optimal density to each element and the standard deviation given by this parameter p. And we had to increase p to these values to see sort of any degradation in performance. So the waveguides are really resistant to random perturbations, and the multiplexer is likewise very resistant with p-value required of 0.34. So the results in all these with all these non-ideal factors considered have encouraged us to go ahead and build the experiment. That's what we're working on right now in the lab. But one thing that's interesting to look at for the future is, what's the limit of what this type of configuration can achieve. So we went ahead and removed all these non-ideal factors and just with the same 10 by 10 array. So we remove all these non-idealities. We allow the plasma to be fairly dense. We operate at a higher frequency, and we were able to achieve a fully functional logic gate with this configuration, which is I was really surprised by this because a logic gate is nonlinear operation. And here we have, this sort of very, very simple physics, this simple device with just an array of idealized elements. But in general, of course, we have a lot of work to get here. But seeing this result is really encouraging, and especially once we build this experimental device, we can actually train it in situ. That's another advantage of working with plasmas, and so we might be able to achieve really, really complex functions like this in the future. So we're pretty excited about that. Now, that's all I have to say in terms of the talk. But I did want to say a couple of acknowledgments. One thing I wanted to say about this fellowship is, I really hate cynicism and nihilism, and I felt like in my undergraduate career I've been surrounded with a lot of that, and about our country, about where things are going in general, and at times it's been hard not to be cynical myself. But I just wanted to say that when I come to this conference, and when I see all the things that you guys are working on and all the people who put this program on, you guys make me really proud to be an American, and you push all the cynicism away. So I just want to say thank you to all you guys, and if you guys have any questions, I'll accept those now.